Hello and welcome to the heat transfer course Convection. My name is Wilko Rovs, and in this video we will look into the topic of forced convection, specifically the internal flow configuration, and we would look at the two different types, the fully developed flow and the developing flow, as well as the caloric mean temperature. The learning goals are as follows. First, we will learn the knowledge of the essential differences between external and internal flows. This requires an understanding of the hydrodynamic and thermal inlet behavior. Later on, we will look at the caloric mean temperature, how to calculate this, and how to apply this caloric mean temperature. And finally, I would like to go in the ability to calculate the local temperatures and heat fluxes, as well as the average heat transfer coefficient for a constant heat flux boundary condition on the side walls of a pipe flow. Let's go into this classification of flows. This picture I think is very clear to you. You have seen it a few times before. So we are now here in the range of internal flows, and we do not treat the topic of free convection, so we are in the forced convection domain where the flow is driven by a pressure gradient applied by the outside. Let's look at the distinction between the external and internal flow configuration. This image here represents a plate flow. This here is a heated plate. We have velocity flow coming from the side, and before the fluid hits the wall, the velocity is more or less uniform, and then as soon as it approaches the wall, you are familiar with that from the last videos, we have the developing of a boundary layer, of a hydrodynamic boundary layer, as well as of a thermal boundary layer. Important here is for the external flow that far away from the plate, the velocity u infinity as well as the temperature T infinity remain constant. So these values apply all over the plate, independent from the distance. This also causes a continuous growth of the two boundary layers. So although you see that the growth decreases, it increases first rapidly and then less and less, there is a continuous increase and a never stopping development of this boundary layer. This also leads to the fact that there's always, independent from the velocity that we apply here, a transition to turbulence after a specific length of the plate, which we call the critical distance. Even for very slow flows, this will happen if the plate is sufficiently long. And to calculate the heat transfer, we have the relation here. The heat flux is equal to heat transfer coefficient times the area of the plate times the difference between the wall temperature and the temperature T infinity. Now let's look on the other side to internal flows. Here we have maybe a pipe flow or maybe a flow between two plates which are heated from the sides. The continuous and never-ending growth of the boundary layer that we have in external flows cannot happen here in internal flows, because these boundary layers, they will grow towards each other and then they will hit each other, and there is no chance of the boundary layer to further grow. So the boundary layer growth is of course limited by the geometry. The second part is that the mean flow velocity, the mass flow that we have going in here, will remain constant due to mass conservation. So if we have a uniform velocity profile here and the velocity on the sides are reduced because of the no-slip boundary condition, this immediately leads to a growth of the velocity in the center. So further away here in the pipe, the velocity in the center will be higher than u infinity, because the velocity here on the wall is much lower, or even at the wall itself 0. The next important part is that the laminar or turbulent flow is decided by the geometry and the channel size, so the channel height, and is not necessary that the flow becomes turbulent after a sufficient length. So the flow can be turbulent if, for instance, for a pipe flow, the critical Reynolds number is surpassed, or it remains laminar if we are below this critical value of roughly 2300. We have to calculate the heat flux from T-wall to the fluid flow temperature. We have to look at another way of defining the temperature, the reference temperature inside the fluid. So the temperature T infinity will not remain constant. Also, the temperature in the center line will increase, and as such we have to look at the new definition, and for this we will introduce the caloric average temperature. And this temperature will increase while the flow is going through the pipe. And finally, what we need, but this will be part of the next video, is a logarithmic mean temperature difference if we apply a temperature boundary condition here. So let's once look again at the two cases. So we have here the hydrodynamic inlet length. You see the uniform velocity profile at the beginning of the flow will change towards a parabolic velocity profile further away, and this profile will remain constant. And in this way here, contrary in the thermal inlet length, of course, the boundaries also grow together, but the temperature profile will still increase in its mean temperature, but the same as is here, the profile itself will remain constant, as you will later see that. So let's go for the next, because this here is a similar representation, but a few important ideas. So first of all, if we are in the fully developed region, the velocity profile is invariant in flow direction. So we always have the same velocity profile with the same boundaries, that the velocity at the wall is 0 and that we have a parabolic profile. This also results in the fact that the wall shear stress is not a function of the spatial coordinate anymore. So we have a constant wall shear stress along the pipe. This will not happen in case of a temperature, because we have a continuous increase in the temperature, so there will be an increasing temperature at the wall and also inside. So let's look at this here. The problem is now the temperature profile is not independent of X, also we are in the thermally fully developed region. The temperature rises due to the wall side heat flux in axial direction. So the temperature is not fixed at the wall, unlike the velocity. What we want to achieve is a representation that is universally applicable. So we look for a definition of temperature profile such that the heat transfer coefficient becomes independent from the location, and to be consistent in this way with the wall shear stress. The solution to reach this aim is to define a proper reference temperature here as Tm, which is now a reference temperature inside the fluid, because this other temperature is T-wall and the heat flux is then the heat transfer coefficient times the difference between wall temperature and reference temperature. And this reference temperature we will look at in the next few minutes. And in order for the heat transfer coefficient to be constant at a constant heat flow, the mean temperature must increase in the same way as the wall temperature. So what type of temperature can we apply here? And this temperature is called the mean caloric temperature. You can see the mean caloric temperature as the mean flow of enthalpy going through a cross-sectional area. How to calculate that temperature? So to calculate the mean temperature, of course, we need to do some kind of integration. What is the enthalpy flow through the cross-sectional area? It is the enthalpy flow at a specific location, so at the radius, which is then the velocity times the heat capacity times the temperature. And we have to integrate that across the pipe, so across dA, and the area is 2 pi r, which is a circumference, times the infinitesimal element dr. If we do that, we can say that the mean caloric, flow of enthalpy is also the mass flow times the heat capacity times an average temperature. And we are interested in this average temperature. So to calculate this average temperature, we divide by the mass flow and the heat capacity and multiply this by this integral expression, which we can solve for in case of a simple pipe flow. And so in this way, we can also express the mass flow by the velocity times the area times the density, and we can cross this out so it becomes a little bit easier to calculate. In the next step, we look at the change of the temperature in a pipe flow with a constant heat flux. How to determine the actual temperature profile in the pipe and outlet, and as well the outlet temperature. To do that, we do what we always do, we apply an energy balance. You can see here our control volume, and we use this infinitesimal control volume, as you can see, and in the next step then we have to integrate to get the temperature profile inside the pipe flow. So what are the important fluxes? Of course, we have an ingoing enthalpy flow, we have an outgoing enthalpy flow on the other side, and we have an ingoing heat flux from the outside towards the pipe. We have done one important assumption, and we assume that the flow is so fast that the thermal conductance inside this fluid in axial direction is negligible. Otherwise, we would have to add here also the conductive heat flux going in and going out. The energy balance just becomes then the one that is shown here. So 0, because there is no change in time, we are looking at a steady state condition, is equal to the enthalpy flow going in minus the enthalpy flow going out plus the flow from the side. Defining all those flows is a rather straightforward manner. So for the enthalpy flow going in, it's a mass flow times the heat capacity times the average temperature. The flow going out is the mass flow times the heat capacity times the average temperature or mean temperature, not at the location x, but at the location x plus dx. And the ingoing flow, the heat flux from the outside, is the heat flux, the boundary condition, so the area specific heat flux times the area, and the area itself is the circumference of the pipe, so P times D times the infinitesimal element size dx. Plugging in these definitions in the equation, we get to a differential equation, which is 0 is equal to the following term. And we can see that we have the change of the temperature here, dm dx, is, if we bring this to the other side, equal to our boundary condition, a prescribed heat flux, times the geometric parameters. And if we also bring this to the other side, we have divided by the mass flux, or it is, if we combine these two together, it's the flow of heat capacity. And you can see this here is a constant because we assumed a constant heat flux at the boundary. And so this results in a constant increase of the mean temperature due to the constant heat flux that we apply to the sides. So a linear increase in temperature. Now we have this equation. Let's look at the boundary conditions that we need to apply. So first, at the location x equal to 0, we have the inlet temperature. So if we integrate this here once, we have to find one constant, and this constant is equal to the inlet temperature. And the outlet temperature is now, if we plug in Tm is x equal at the location x equal to L, we get the outlet temperature. to be this constant coefficient times the length plus the inlet temperature. And the wall temperature, if we are looking at the wall temperature, we have the heat flux that is prescribed is equal times the heat transfer coefficient times T wall minus Tm, and we can replace this to get the wall temperature is equal to Tm plus the heat flux prescribed divided by alpha. But interestingly, we don't know this value of alpha yet. So how to determine this heat transfer coefficient alpha? This will be shown in the next videos. We have looked at the mathematical derivation. Now let's do some kind of drawing and look how we can draw the temperature profile inside the pipe in axial direction. So we have the temperature, the coordinate x, and what happens here at the beginning. Of course, the temperature of the fluid at the beginning, at the wall and in the center is equal to the inlet temperature. And then it will continuously increase. So we have here our fluid temperature, which is linearly increasing due to the constant heat flux. Now, what happens with the wall temperature T wall? It is not fixed because we apply the constant heat flux boundary condition. So looking at the distribution of the wall temperature in axial direction, we know that if we come in here with the temperature over the whole part distributed being the temperature T fluid, the inlet temperature, then the wall temperature will also be very close, or even mathematically at x equal to 0 will be the same as the fluid temperature. But then the wall temperature as well as the thermal boundary layer increases drastically in the beginning and then approaches a constant value, especially the one that is needed to transfer the heat that we have as a constant heat flux from the wall into the fluid. And this difference here we call the pinch, and this pinch depends on the thermal conductivity of the fluid, the heat capacity of the fluid, then of course on geometry like channel size, and on the velocity of the fluid inside the channel. To calculate the heat transfer coefficient, or to at least draw the heat transfer coefficient, we rewrite the general equation to alpha is equal to the heat flux divided by the area times the difference between wall temperature and fluid temperature. And we have both the wall temperature here and the fluid temperature, so we should be able to make at least a drawing for the heat transfer coefficient alpha, although we don't know how it looks like mathematically. If we do that, we start here at the beginning. We have a very low difference, even nearly no difference, which means that we start with a very high value at x around 0. Then the temperature, the heat transfer coefficient decreases continuously until it reaches a constant value, and this value depends here on the pinch. So we have this classical curve which starts at an infinite value at x equal to 0 and ends at a constant value for larger x values. To bring this in a mathematical way, I don't want to go into the derivations of these equations, so we have here prescribed that alpha is equal times the constant times the flow of heat capacity. You can see rho CPU is just the flow of heat capacity divided by the geometry, the diameter of the channel, times the thermal conductivity. So all these important information are also in here, and then it decreases by 1 over x. Finally, we will reach a value which is a constant C2 times the thermal conductivity divided by d. And you can see that here in the constant value, it is interestingly independent from the velocity profile and the flow of heat capacity. So it only depends on the diameter of the channel and the thermal conductivity. Now let's finalize this video with a few questions of understanding. So first, what is the difference between external and internal flows? From my perspective, the main difference is the way we describe the temperature, the reference temperature for calculating the heat flux. For external flows, this is pretty simple. It is just the outside faraway temperature T infinity. For internal flows, because the boundary layers grow together and the mean temperature increases over the whole pipe length, we have to use another way. We have to use the caloric mean temperature. What's the meaning of the hydrodynamic thermal entrance length? So within the entrance length, we know, or we have learned, that the shear stress changes, it decreases until it reaches a constant value. And the same happens with the thermal entrance. Within the thermal entrance length, here the heat transfer coefficient starts with a very high value, even infinity at x equal to 0, and then drops and approaches a constant value. What is the meaning of the caloric mean temperature and how can it be calculated? So the caloric mean temperature, if you want to ask me for a meaning, I would say, okay, let's take the fluid flow exiting a pipe and pull it into a bucket. And then we steer this bucket and look what is the mean temperature that comes out. So it's actually the mean temperature of the fluid if it is perfectly mixed. The problem in the pipe flow itself is that we have a layering. Outside, close to the wall, we have a different temperature than inside. But on the other side, we have a very high velocity inside the pipe, but a low velocity outside. So we have to calculate the mean temperature by integrating the enthalpy flow across the pipe. How does the local heat transfer coefficient change inside a laminar pipe flow? We have discussed that already in the question before. So the local heat transfer coefficient starts very high, mathematically at x equal to 0 at infinity, and then drops towards a constant value that depends on the geometry that we are looking at. So for instance, for a pipe flow, we have a specific value, and for a flow between two plates, we will reach another value for that. And with that, I would like to thank you for your attention. Have a nice day.